All right, so today what we're going to be doing is the lab, the Earth's Shape. All right, the Earth's Shape lab. So we're going to look at two things today. First off, we're going to look at describing the true shape of the Earth. Now, by now you should know that the Earth is an oblate spheroid, meaning it's slightly flat at the poles and bulging at the equator. We're going to look how you can accurately describe that. And then we're going to look at how smooth surfaces on the Earth should be represented. All right, so first off though, an oblate spheroid is flat at the poles and bulging at the equator. Now you can describe both these features right here as oblate spheroids, but obviously one of those is flatter than the other one. So to more accurately describe the shape, we use something called the roundness ratio. And what the roundness ratio is you measure the polar diameter, which goes from North Pole to South Pole. You measure the equatorial diameter, the distance along the equator. You divide those, and it gives you a number. The closer that number is to 1, the more like a circle it is. So, I'm going to take my ruler out here. And for example, this guy right here, I measure that. So my polar diameter is going up and down. I measure my polar diameter and it works out to be 10 centimeters. Equatorial diameter is going from there to there. I measure that and it works out to be about 13 centimeters. I pull out my handy dandy calculator. I go 10 divided by 13. The roundness ratio of this guy right here is 0.769. All right. Now, that number is kind of meaningless unless I got something to compare it to. So let's compare it to this guy right here. All right. Polar diameter is that number right there. So I measure from there to there. And I get 8.5 centimeters. Measure it from there to there. Equatorial diameter, and I get about 19 centimeters. So I do 8.5 divided by 19, and I get 0.447. So what you should notice between those two right there is that this one has a higher roundness ratio and it looks more circular. This one has a smaller roundness ratio and it's flatter. Now the roundness ratio of a circle is 1, so the closer that number is to 1, the more like a circle it is. The smaller it is, then the less like a circle it is. Okay. So first off, what we're going to do is you're going to calculate what the roundness ratio of the Earth is. So in your lab, right here, the top part is what's right there. All right. So you want to calculate the roundness ratio of the Earth. So I've given you the polar diameter, I've given you the equatorial diameter. So what you need to do is plug those numbers into this formula right here. And you want to calculate the roundness ratio to the nearest thousand. So nearest thousandth means you're rounding it to the 3 places out, like I did right there and right there. So round it to the 1,000th place. So that number divided by that number. It should have worked out to be like 0.9 something or other. All right, so you should have that by now. All right. Next, all right, so we want to compare that to something. So in your lab, you have a diagram of the Earth here. You have a diagram of the Earth, and All right, and we want to compare the Earth's roundness ratio to that diagram that is in your lab. All right. So, using a ruler, and there's one in the front of your reference tables, if you need to use that. You want to measure the polar diameter. So on your diagram, you want to measure this in centimeters to the nearest tenth of a centimeter to give you that number right there. Next, you want to measure the equatorial diameter in centimeters. So for this number right here, you're going to use your ruler and measure across like that. Again, to the nearest tenth of centimeter. And then what you want to do is you want to calculate the roundness ratio. So again, using this formula right here, polar diameter divided by equatorial diameter, you're going to take this number right here and divide it by that number right there, and then record your roundness ratio to the nearest thousandth. Now notice, one thing I forgot to mention, there are no units on roundness ratio because I'm taking centimeters divided by centimeters. So the centimeters, when you divide them, cancel each other out. So it's just a number. There are no units on roundness ratio. So I'll give you a little bit of time to do that. All right, so if you've done your calculations properly, what you should have noticed is that both these numbers should be less than 1, but both of them are really close to 1. All right. However, if you had to pick one of them to see which one's closer to 1, this one should have came out closer to 1 than this one did. Now, the point of this is that if you were to look at this picture and someone were to ask you what shape that was, you'd probably say a circle. But when you look at your number that you got right there, you should have found out that your roundness ratio is not 1. So that means it's not a circle. But this number is close to 1, so it's almost a circle. Now the Earth is even more like a circle than that diagram right there is. So the moral of the story is that, again, the Earth's an oblate spheroid. It's shorter at the poles and bulging at the equator, but it's only a tiny amount. It's not an amount that you can see with your naked eye. It's an amount that can be measured, but you don't notice it with your naked eye. All right. Now, so that's the first part of the lab. Second part of the lab. All right. Now, on your diagram you have there, in the upper right-hand section, there's a little diagram of Mount Everest. Now, what that represents is when you buy a globe, like this kind of globe, quite frequently, it has little bumps where the mountain ranges are on them. All right, so I can go like, ooh, there's the Himalayas, or ooh, there's the Rockies. Now, these bumps on here are actually a lot bigger than they should be if this was made to scale. So if the mountains were made at the same scale as the rest of the globe, these mountains would be a lot smaller. All right. So since we can't give everyone a globe to work with, what we have is this diagram here. So this diagram represents a globe, and it has like the little bumps on it to represent the mountains. So what we want to do is we want to figure out, because right now Mount Everest on that diagram is a lot bigger than it should be if it was drawn in actual scale. So what we want to do is we want to figure out how big should Mount Everest be if it was made to actual scale. All right. So I'm going to walk you through calculations. I'm not giving the answers, but I'll walk you step by step what you have to do. All right. So again, you're going to need a ruler for this. Okay. So step 1. Height of Mount Everest in diagram. All right. So you want to use your ruler and go to Mount Everest in the diagram right there, and you want to measure precisely how big Mount Everest is. It should be like 0 point something centimeters. Okay. That's the number you're going to write right there. So you want to measure how big, how tall Mount Everest right there is in centimeters. It should work out to be 0 point something or other. All right, step 2, actual height of Mount Everest. Because I'm a swell guy, I'm just going to tell you what that is. The actual height of Mount Everest is 8.8 kilometers. Step 3, it says the average diameter of the Earth calculated from the data above. All right, so we have the polar diameter, that's this way, equatorial diameter, which is going this way. So what we want to do is we want to calculate the average between those two numbers. So what you want to do is take this number plus this number, hit equals, and then divide by 2. That'll give you the average. So that's going to be what you're going to write for that number right there. Average diameter of the Earth. So for line 3, you're going to take that number plus that number, hit equals, then divide by 2 for the average. That gives you that one right there. Step 4, average diameter of Earth's diagram. All right, so you're going to do almost the exact same thing that you did for 3, except for using those two numbers right there. So you want to find the average of those two numbers, and that's going to be what you put on line 4. Okay, next for line 5, it says correct scale for Earth diagram Mount Everest. This is what we're trying to find out, is how big Mount Everest should be in that diagram if it was made to actual scale. So how we're going to figure that out is we're going to use this proportion over here. We're going to use this proportion over here. And we're going to substitute numbers that we have over here into this proportion so we can solve it out. All right, so first off, what we're trying to find out is how big Mount Everest should be on that diagram if it's drawn true to scale. Right? So of these things here in this proportion, so it's actual size of a feature over the average diameter of the Earth is going to be equal to the surface feature on the diagram over the average diameter of the Earth's diagram. What we're trying to figure out is how big Mount Everest should be on that diagram. So that's going to be surface feature on the diagram. So that's going to be X right there. That's what we're trying to find out. Actual size of the surface feature. That's going to be the actual size of Mount Everest. So that's going to be the number from line 2. So the number you have on line 2 over there is what you're going to put on that blank. Okay. Next one, it says average diameter of the Earth. All right. That's going to be the number you have on line 3 right there. Next, it says average diameter of Earth's diagram. Average diameter is Earth's diagram. That's going to be the number you have on line 4 right there. Is what goes right there. So now I want to solve it for X. I want to solve it for surface feature on diagram. So that's what the height of Mount Everest should actually be. So if I want to solve it for X, I need to cross multiply and divide. So it's going to be the number from line 2 times the number from line 4 divided by the number from line 3 will give you X. All right, so that would be the number I get right there. So the number from line 2, that one, times the number from line 4, that one, divided by the number from line 3, that one, solves it for X. So that would be the correct scale for the Earth's diagram in Mount Everest. Now I'll give you a hint, it works out to be like 0.0 something or other. Right? So it's gonna be a really small number, 0.0 something or other. All right, now the last thing we want to do is we want to calculate the percent error of the size of Mount Everest in that diagram. So in this diagram here, you should have found out that Mount Everest is a lot bigger than it should be if it was drawn true to scale. Right? This is a lot bigger than it should be if it was drawn true to scale. So we want to figure out what the error is of that drawing. So a little bit backwards from the last topic, if you remember the formula for percent error, is the difference between the measured and accepted over the accepted times 100. So we're going to use this formula, but we got to figure out what's the measured and accepted over here. All right, so the accepted value is going to be what the correct scale of Mount Everest should have been. So that's going to be number 5, correct scale of Mount Everest in diagram. So that is your accepted value. All right, so the number from line 5, that's your accepted value. So that's what the number you want to plug in there and there in the formula. The measured value is how big the feature is in that diagram. So that's going to be the number from line 1. Right? So the number from line 1 right there is going to be the measured value. Right? So then you can solve it out. So you got the measured value, number from line 1, minus the accepted value, the number from line 5. You subtract those two, get equals on your calculator. Then you want to divide it by the accepted value, the number from line 5, times 100 will give you the percent. I'll give you a word of warning, the percent works out to be over 1,000. Right? So you didn't do anything wrong, the percent error in that diagram is over 1,000. Which tells you that that little feature right there is a lot bigger, is a lot bigger than it should be. All right, so and then on here it says you need to show your work. All right, so again, your percent error should be over 1,000. Now, once you have this done, once you have your all your data over here done, then you have a few questions on the back. One of the questions has you use this formula again, but you're going to have to substitute different things in this formula, but you're going to use that formula again for question number 5. Otherwise, that's it.